Hi, I'm Miss Boom. Today we're going to sketch the tangent function. First, we're going to use two websites, one to plot it and one to see the clear line and what happens when we reach 90 degrees and 270. We're going to look at a unit circle and we're going to plot each of the points and see what it looks like. Let's use GeoGebra. So let's start by sketching a tan graph. Recall from the last video that the tangent is this little line here coming out of 0, 1 that it forms as we go around the unit circle. Or it is also sine over cos or y over x, so the gradient of at that point. So let's start at the angle 0 and we're going to go to 90, 180, 270, back to 360, and we've stretched out our x-axis to reflect the same values. So let's go from 0. As we get close to 45 degrees, we know at 45 degrees tan is 1. So as we get to 45 degrees, we notice that tan is 1. But as soon as it goes past 45, we can see that it's becoming very big very quickly. See, tan is getting really big. So we're just plotting the points, each of these points, and we see that it gets to a point where at 90 degrees it's undefined. We have no value there. And then past 90 degrees we're really big and negative, really huge. And then as we approach 180, we approach 0 because tan at 180 is 0. And as we go past 180, we're no longer negative, we're going to be positive. So a little bit positive, see the tan there. And then as we go more and more closer to 270, we get really big. So the tan value gets really big really quickly. Then again undefined. And as we get close to 360 in the fourth quadrant, tan is negative. And as we get to 360, we get close to 0. So here we plotted all the points. Let's go to this graph and let's do the same thing, but this time we're plotting in something else. Oops. As we get to 90 degrees, we have the asymptote. And again, at 180 it's 0, but as we get to 270, we have another asymptote. So here we have the asymptotes where tan is undefined. So here we have the x values, and recall from learning about exact values what tan of these points are. If you've forgotten, please revise that. It's important that you understand, otherwise it will be very hard to plot these and find intercepts. So when x is pi on 2, what is tan? Well, a pi on 2, tan is always undefined. It doesn't matter if it's negative or positive. When x is pi on 4, we know that tan is equal to 1, but negative pi on 4 means we're in the 1, 2, 3, 4, fourth quadrant, and tan in the fourth quadrant is negative. So negative 1. At 0, tan is just 0. At pi on 4, tan is just 1. At pi on 2, again undefined, and etc. etc. Now we're going to look at whether it has an amplitude. Now tan looks like this. So it keeps going, and unlike cos and sine, it does not have a maximum or minimum, so we don't describe that as having an amplitude. What about 2 tan x? How does it differ to tan x? Well, 2 tan x will look like that blue line over there. So we can see that it's a lot steeper than tan x. The 2 tan x is steeper, and we can say that it's dilated from the x-axis as well. What about half tan x? Will it be steeper or less steep? It would be less steep, so it will look like that. So it's hard to see the difference when you're sketching just a single graph because the amplitude doesn't change like sine and cos, but the steepness changes. What about 3 tan x? It will be more or less steep? It will be steeper, so it looks even more vertical. So we can see that there's x-intercepts at 0, pi, 2 pi, and 3 pi. So every pi whole number, or in other words, the x-intercept occur at x equals k pi, where k is a whole number. And in between these x-intercept, right in between, we can see that that's where the asymptotes are. And the asymptotes occur at pi on 2, 3 pi on 2, 5 pi on 2. Or in other words, every odd number divided by 2, 1, 3, 5. So 2k plus 1 over 2 pi's. So memorize these two boxes, they'll come in very handy. So we describe these values in front of 10x as a dilation from the x-axis, and we can observe that it changes the steepness or the shape of the graph. So we have talked about A, now we're going to talk about N, or how does it change the period. Now if 10x looks like that, where it repeats itself every pi, so it's periodic at pi, then we can also observe that the asymptotes repeats itself after pi, so a half pi, and then plus a pi is 3 over 2 pi. So a half to 1.5, there's a difference of 1. There's a difference of 1. So you can see that there's a difference of 1 between two exact points. So the period is pi. What about if we had tan 2x? What would it look like? It would look like that. And we can see that the period is different now. It's much faster. It's as if the graph has been compressed this way. So it repeats itself at not pi, it's done it twice, at half of it, pi on 2 or 2 pi on 4. So the period now is pi on 2. So in other words, that little 2 affects the period. What about the x-intercept? Now that the period is every half pi or k pi over 2, then the x-intercepts happen What about the x-intercepts? Well, the period repeats every pi on 2, so the x-intercepts will also be pi on 2 times k. Let's test that out. When k is 0, we have 0. When k is 1, we have pi on 2. When k is 2, we have 2 over 2 is 1, so pi. So the x-intercept is k pi on 2. What about the asymptotes? Well, that's halfway of that. So now it's 2k plus 1 over 4 instead of 2 like before. So can you start to see the pattern? So instead of, we are adding this 2 at the bottom, the denominator. So let's talk about what happens if we have a half x. What would it look like? It would look stretched out like that, or would look dilated from the y-axis that way. And so now when we look at the period, it's no longer pi, but it is 2 pi. The period is 2 pi. So what about the x-intercept? The x-intercept will happen at every even pi, or every 2 times k pi. And we do that because by doing k pi over whatever the number in front of x is. So k pi over a half is the same as 2 pi. And then the asymptotes, instead of being 2k plus 1 over 2, is now just 2k plus 1. And we worked that out because 2k plus 1 over 2 times half is just 1. So let's generalize this a tan and x by looking at tan 2x again. So we observed that the period changed to pi on 2 and that the x-intercept was k pi over 2. So now we're going to memorize it as the x-intercept for tan is always k pi over n, where n is a number in front of x. And the asymptotes was 2k plus 1 over 2 times n, the number in front of x. So memorize these two boxes. Where k is obviously an integer, if I haven't mentioned it already. Let's do an example. Example 1. Y equals 2 tan 3x for x is between 0 and pi. So the period is pi over 3. And we have a 2 there, which is a dilation. So let's look at the x-intercept, which was k pi over n, or in other words, 3. And the asymptotes, it was 2k plus 1 over 2n, and 2n is 2 times 3, which is 6. Now we always write k is an element of z, or every integer. And now we draw our graph. It's between 0 and pi, so 0, we're going to write pi first. Because the period is a third pi, we're going to divide our section into thirds. So we'll have a third pi and 2/3 pi's because we know that's where our x-intercept will occur, because that point will repeat itself at those points. And then we can halve it again to find the asymptotes, or we can plug it into the equation by letting k equal various numbers. When k is 0, 2 times 0 is 0, plus 1 we have pi on 6. When k is 1, 2 times 1 plus 1 is 3, 3 pi on 6, or pi on 2. When k is 2, we have 2 times 2 is 4, 4 plus 1 is 5, pi on 6. So now we have pi on 6 is our first asymptote, and pi on 2 is our second one, and 5 pi on 6. But as I said before, you can just go halfway your period. So half of a third is a 6. And then you count by a 6. 1 6, 2 6, 3 6, 4 6, 5 6, 6 6. Now we have to write let's draw the graph. So it's a positive graph, so it goes down that way. And then we're going to plug in the asymptotes. Don't forget to write the equation of the asymptotes in your graph. Example 2. Y equals negative tan 2x for x is between negative pi and pi. So the period this time is pi over 2. And the x-intercepts are k pi over n, or in other words, k pi over 2. And the asymptote is 2k plus 1 pi over 2n, and 2n would mean 4. 2 times 2 is 4, where k is an element of, where k is an integer. So let's get our graph between negative pi and pi. So now we have our axis looking like that because of the domain. So negative pi to pi. And because we have a period of a half, we're going to cut it into halves, because we know now that it goes between that dot to that dot to that dot, and same likewise on the left hand side. So always use the period to know how to scale your x-axis, whether we're going by halves or thirds or sixths or quarters. So now we do half of that. And why we're doing half of that? Because halfway the x-intercept we have the asymptotes. And notice that I'm not even calculating with k values. I could to check my answers. If the question wasn't asking me to graph but finding the asymptote, then I'll use this equation. But if it's asking me to graph, then I'll just do it directly on my graph. So now we label the asymptotes. Oh, before we do that, we notice that the graph has been reflected. So instead of sketching it going up, we're sketching it going down. And so now we have noticed that it's been reflected. And what else do we need to put? The asymptote equation. So let's put that in. Example 3, sketch y equals tan 3x plus 1 for x is between negative half pi to positive half pi. So the period again is pi over 3. And we're going to write it as 2 pi and 6 as well, because we know that we're going to count by 6 this time. So I always do that. And it's not part of my working out, but it just helps me remember how to scale my x-axis. So let's sketch the domain of negative pi to pi. So again, the y-axis is right in the middle because of the domain. We're going from negative half pi to positive half pi, and we're going by thirds, so we're going to count these into thirds. But because a third of a half is a sixth, that's why that was really handy there. So we have pi and 6 and so pi and 6, 2 pi and 6, pi and 6, 2 pi and 6, 3 pi and 6, which is a half pi. Yeah, that makes sense. Okay, so the original equation that we memorized for the x-intercept was k pi on n, where n is 3. So we could work it out using that. Or we can understand that the period is a third and just go by a third. And we notice that it's being translated up. So now, what happens to our x-intercept when the graph has been translated up? Our x-intercept, so if this was the line going through that point there, when it's moved up, the x-intercept has moved to a different point. So we can't use that anymore, but we can use it to find our original x-intercept, so we know roughly where it is. This time we do know that it's been translated up, means that we know what the y-intercept is. Because if this original point was here, when it moves up, so this point here at 0, 0, when it's moved up by 1, then the y-intercept is at 1. What about the asymptote? Do the asymptotes change? So the vertical line, do they change if you move them up or down? No, they don't. They're still in the same spot. So even though we can't figure out the x-intercept from the equation, we can figure out the asymptote from the original equation. So 2k plus 1 over 2n, where n is 3, so in other words 6, and k is an integer. So let's do that. When k is 0, 0 plus 1 is 1, 1 over 6, or pi over 6. When k is 1, 2 times 1 is 2, plus 1 is 3, 3 pi on 6. When k is 2, 2 times 2 is 4, 4 plus 1 is 5, 5 pi on 6. And can we do that? No, because 5 pi on 6 is outside our domain. But we can go to the left, so let's do that. When k is -1, -1 times 2 is -2, plus 1 is -1 over 6 pi. And when k is -2, -2 times 2 is -4, plus 1 is -3, -3 pi on 6, which is -pi on 2. You might be tempted not to do -2 because you saw the 2 doesn't fit, but remember there's a plus in that equation so that it will change the value. It's not a mirror image. -2k is not a mirror image of the 2. So anyway, let's plug these in. So let's put the pi on 6, pi on 2, negative pi on 6, negative pi on 2 as our asymptotes in there. And let's label them. Now we know where to sketch our graph. Well, we know that it goes through that point over there. So it also goes through that point and through that point. So the original graph went through the point underneath it. The new graph will be going up. Will be the same but up. So let's do that. So now we have to figure out what the x-intercepts are. How do we do that? We do it the same way we have always done it with graphs. We let y equals to 0. So now you can see why knowing the exact values is so important. We have to solve for this. So tan 3x, move the 1 to the other side, becomes -1. How do we solve for this? We let this equal to theta to simplify our calculations, and we substitute theta back to 3x when we're done. So when is tan theta equals to 1? The first quadrant angle would be pi on 4. And which quadrants are negative for tan? That is quadrant number 2 and 4. So now we have pi minus pi on 4 for the second quadrant and negative pi on 4 for the fourth quadrant. So now, well, we're going to write 1 minus a quarter as 3 pi on 4. And we write that, and we notice that we have 2 solutions and we need a third solution. So what we can do going from here to here is to subtract a period, because we're traveling a period to the left from this one, and this one is the -1, so negative pi on 4. So we're going to subtract a period, so pi. And notice that I'm not subtracting that period because we're working with theta, okay? So we're subtracting pi when we're traveling along tan, and we subtract or add 2 pi if we're using sine and cos. So now we have 3 pi minus pi on 4, and minus a quarter minus 1 is minus 5 pi on 4. And now we've got our values, but we need to go back to 3x. So changing theta back to 3x, we divide everything by 3 to figure out what x is. So now we have 3 pi over 12 minus pi over 12 minus 5 pi over 12, because 3 times 4 is 12. So those are our x-intercepts. So let's put these in our graph. So 3 pi on 12 is the same as pi on 4. So let's put that in. And then we have negative pi on 12 will be that one there, and obviously that one will be negative 5 pi on 12. You might want to redo this question again, it's quite tricky. I'll see you next time. Bye!